without the projection. And that actually allows you to find galaxy cluster way to very high redshift with modest amount of resources. Usually you need a relatively big telescope, maybe tens of nights. So nowadays, telescope time costs $25,000 to $100,000 a night. So you spend 20 or 30 nights looking for cluster, it costs a few $1 million. Now, there's also gravitational lensing that allow you to, weak gravitational lensing that allow you to find cluster. But so far, there haven't been a really successful survey to find new cluster based entirely on this weak lensing methods. But those days will probably come. There are advantages and different advantages to each one. This method, which I don't have time to go into, you can come and talk to me about it. So, as I mentioned, the two surveys that I'm going to focus my talk on today is the SPARCS and the GCLASS survey. So SPARCS survey was started by my former PhD student, Adam Wilson, who's now at Cambridge. It stands for Spitzer Occultation of the Red Sequence Cluster Survey. What it does is that it uses imaging data from the Spitzer infrared telescope, which is a relatively small telescope, the real size about this big, which give you images in 3.6 micron in the infrared, and we combine them with ground-based telescope at 0.9 micron, or 9,000 angstrom, in order to form a color pair that allow you to identify the red sequence at very high redshift. It's not a very big survey, so only about 42 square degrees compared to 1,000 square degrees that we done using just optical data. But it allows us to identify a very significant number of galaxy cluster candidates redshift bigger than 1. Now, 15 years ago, when we first started using this red sequence method, there were only about 5 or 6 galaxy clusters known at redshift 1. Now, there are basically hundreds. And so these are the actual field of the SWIRE surveys. The SWIRE survey is a publicly available survey of these 5 fields, or 6 fields that is done by a different part of the sky. That's done by Spitzer, and we combine them with our own optical data. But the majority of data actually come from what we call the GCLASS survey, the Gemini Cluster Astrophysical. So basically, it's a public survey. What we did is we picked 10 of the richest cluster at around redshift 1 that we found using the SPARCS cluster. And then we go to the Gemini 8-meter telescope, one in the north, one in the south, and we do multi-object spectroscopy of galaxies in the cluster field to get spectroscopy of the cluster galaxies. And multi-object spectroscopy is actually a very neat technique, which I don't have time to go into, but it allows you to point your telescope at a cluster, and you can put a slit in the focal plane where there's a galaxy, and pipe the light through a spectrograph, and you get many spectra in one shot. So this is a CCD image of exposure where every one of these long rectangles is actually a spectrum. The little dash thing you hear in the sky are the absorption emission lines for the sky. So every time you take one exposure, you get spectra for about 50 galaxies simultaneously. And this allows you to do many galaxies at the same time. So this survey, which took about 240 hours of Gemini time, provided us with 437 cluster members, redshift. I mean, out of these 9 clusters, we have 10 clusters, but we didn't use the one in redshift 1.35. There are not many redshift in this cluster. Out of the 9 clusters between this redshift range, we managed to obtain 437 cluster members. And what this means is that when you look at a cluster, you don't really know which galaxies, necessarily know which galaxies in the cluster, because remember all these galaxies between you and the cluster are projected, or even behind, are projected onto your image. And you can only know for sure by taking a spectrum of a galaxy and measuring how much the spectrum has shifted. And you can identify your cluster member that way. And after, essentially the equivalent of 6 hours per night, 240 is 40 nights of telescope time in these very big telescopes. We managed to get 437 galaxies measured with redshift at these cluster redshifts. And this actually is still the largest such sample in the world at this point, although we're going to beat it with our own mixed project. So this is what these clusters look like. So here are 9 clusters. They are colored, false color images, in which galaxy that look red is actually in red color. And you can see that, these are center of the cluster, obviously. You can see the cluster. They show up as red galaxies because most of them are red at that in the infrared redshift. And each one of this is about 3.5 megaparsec in size. So R200, remember, is about 100 megaparsecs over this big. And now, even with that much telescope time in 8-meter telescope, we can measure spectra with enough feature to figure out the redshift. Many of them are still too noisy to actually measure the property of the spectrum by measuring what's the equivalent width of absorption emission line, etc. And what we end up doing is actually stacking all the spectrum together to get better signal to noise. And this shows you what happened when you stack all the spectral member for the 901 for the 437 spectra, separated by different property. And essentially, what we do is we divide this set here by looking at how far is it away from the center of the cluster. So these are galaxies that are very close. There are 105 of them that are within 200 kiloparsec of the center of the cluster. The next set, the yellow, it doesn't show up very well, is 144 galaxies spectra stacked together, etc. And these are the most distant one from the cluster, bigger than 750 kiloparsec. There are 93 of them. These are what we call field galaxies. They're just galaxies sitting outside the cluster, not really related to the cluster at all. And similarly, you can also separate them by how heavy or how large the galaxy is. So these are the most massive galaxies with stellar mass within the 10 to the 11th, etc. And these are the least massive galaxies. So the main thing here is that you see whether you're close to the center, whether you're looking at a very massive galaxy, the spectrum's main feature is this 2 absorption line here, which is calcium. And the other thing is that this is oxygen 23727, the forbidden oxygen 2 line, which we take as an indication of star formation. Oxygen 2 primarily created by shock and some reionization from star formation. And the larger it is, usually means there's more star formation going on. And you can see how you go from a lot to almost none in the center, or you go from a lot in low mass galaxy to almost none in massive galaxies. So that is sort of what the basic data look like when you stack them based on in different bins. Now, so this is the same plot, and now we can from these stacked spectrum we can measure the various parameters that tell us something about star formation in these galaxies. So what's plotted here, you can look at these 3 first. On the bottom, we plot the star formation fraction. So you have all your galaxies in as a function of radius from the center of the cluster. This is the field outside the cluster. And you basically count how many galaxies I have that have star formation, which means some oxygen 2 emission line of, in this particular case, of 5 angstrom equivalent width. And so you can see that in the center, you only have about 20-some%. This is roughly what you make. And as you go out to the field, it's almost 100%. It's 90%, 80%. So most of the galaxies out at the edge of the cluster or in the field have O2 emission line, indicating that there's star formation going on. And the typical star formation rate is a few solar mass per year. Just to give you a reference, our own galaxy, our own Milky Way galaxy is forming stars at about a solar mass per year. Now, and if you look at the actual star formation rate, which is saying what is the total amount of star formation in solar mass per year as a function of radius from the center or distance from the center of the cluster. And you can also see that it's relatively low, typically about 1, and it sort of more or less double by the time you go out to the end. The number that we use the most is actually this one. It's called the specific star formation rate. It is the star formation rate normalized by the mass of your galaxy. So obviously, a bigger galaxy, with the same star formation rate is actually having equivalent of less activity than a small galaxy with the same star formation rate. And here we also see that as you go out in distance, in star formation rate per unit mass is also increasing. And here one plot this against mass, where the purple line represent galaxy that's in the cluster. They're all in the cluster, not separated by radius. And the green line represent galaxy that actually not associated with the cluster, just out in the field. And you can see typically the green line and the purple line follow each other, except in the cluster everything is lower. So this is more or less the same as what we know in lower redshift, in redshift 0.5 even today. And now the thing is, we really should look at this because you can see that they're both dependent on distance from the center of the galaxy and also on the size of the galaxy. I mean, distance from the center of the cluster and also the size of the galaxy themselves. So the thing that you really want to do is to control for one of the parameters. So for example, you can measure what happened to star formation rate as a function, or star formation fraction there, as a function of stellar mass, but for galaxies at different distances from the center of the cluster. And you can see that they, as a function of mass, the more massive galaxy will have fewer galaxies that are forming stars. But then, if depending on where they are different. And here, similarly, as a function of distance from the center of the galaxy cluster, is galaxy of different masses, the most massive, intermediate mass, and the least massive. And so this is for star formation fraction. This is for the specific star formation rate. And here, what we find is that when you plot it against stellar mass, they more or less are the same as a function of stellar mass. It doesn't really matter that much whether a galaxy is sitting at different distance from the center of the cluster. And here is just another way of plotting all these data points. We plot it against distance from the center of the cluster for galaxies of different masses. These the less massive one, the intermediate mass, and the very massive one. And essentially, they don't change a lot. They might change by 0.2 dex kind of thing. And now, what this is saying is that because of the fact that galaxies of the same mass seem to have, if they're forming stars, they seem to form stars at the same rate per unit mass. And that means if they are switched off, they must have gone to 0 very quickly. So this plot does not include galaxies that already have no star formation. Only galaxies we can see star formation. And so there isn't some sort of intermediate stage where as they, let's say you pick a galaxy, a very massive galaxy, or a intermediate galaxy, it will continue forming stars at the same specific star formation rate, and then we just die very quickly. You don't see things drop slowly as they go toward the center. And we interpret this as that when you turn the star formation off, it's like turning a light switch off. So it's not like star formation will dim slightly, slowly over time. But when you turn it off, star formation will stop very quickly. And of course, very quickly is an astronomical term. It turned out to be a few hundred million years. So for us, it's very long. For the universe, it's not. So this is sort of one of the major conclusions coming from this. Now, there are other things we can look at. One is the type of galaxy that's called post-starburst galaxy. It turned out when you turn off the star formation in a galaxy, as I mentioned before, the very massive stars will die off, and the less massive stars will take much longer, basically almost forever to die off. So about 1 billion years after you turn off the star formation, the only star you have left, the brightest star you have left is what we call A star, which is star that have spectrum that look like this. These are primarily Balmer lines. And we call these, so when a galaxy is forming star very strongly, you turn it off, in about 1 billion years, the spectrum will look like this. So by looking for these spectrum, we can actually try to figure out what are the objects that are, maybe half a giga-year ago, or a giga-year ago, they were still forming stars, and now they look like this. And when we can identify about 28 of these only out of the 400 some stars. And so the signal noise is relatively bad. But when we plot them to see where they are, as a function of where they are, you can see that in the field, there are very few of these. For a massive galaxy, there are very few of these. They're mostly near the middle and mostly in the lower mass star. So what this is saying that when a galaxy happily forming star out in the field, they're not being quenched, so you don't find any of these post-starburst galaxies. But once they come in, it doesn't seem to affect the most massive galaxies. You still don't see any post-starburst galaxies. But in the lower mass galaxy, you see a lot of these galaxies that happen to be turned off not long ago. And it mostly occur in the lower mass galaxies. Now, so we decide to look at where are these 28 also galaxies seated in their cluster. So in this paper by Adam Wilson et al., we plot their position, which are marked by these green circles, of these post-starburst galaxies as a function of distance away from the center and as a function of their relative velocity to the center velocity of the cluster. So this is all adding all the 9 clusters together to get a single noise. And what we notice immediately is that it actually avoids this region. Okay, so there are some they're close to the center, but the velocity is not close to the velocity center. And this, we feel, will actually tell you something about why or how long it takes for a star to go from the blue spot to the red spot. Here, the blue spot is star forming, and the red spot are galaxies that are not forming stars. And what we did was we take a bunch of n-body simulation and simply what we call hand painted in or just put in a parameter when a galaxy would turn off its star formation, and then we would set basically where they would turn off the star formation at 1 R 200, 0.5 R 200, 0.25 R 200. We also set the time scale, how long for a galaxy to turn red once you turn off the star formation, from basically very short time scale out to more than 1 gigayear. Here is 0.1, about 0.1 gigayear. And we look at how these post-star burst galaxy would be situated. And by doing a 2DKS test, we find that these 4 set of parameters actually have some similar to the actual data. And in fact, the best fitting one is here compared to the actual data. And you can see how the green, which you may not see very well, avoid the center. And this happens to have a parameter where you turn off the star formation when the galaxy hit 2.5 R200, and you let the galaxy would die off, become red in about somewhere between 1 to 0.5 gigameter. And so these galaxies actually tell us approximately when, on average, the star formation will be turned off and how long it takes for the galaxy to die off. Another way of doing this is by looking at the spectrum of star forming and post-starburst galaxies. If we assume the star formation history looks something like this, where the star forming galaxy that are falling in are forming star at this rate, so slowly declining. And then when it hit the cluster, it would drop very rapidly into very low star formation, 10 to minus 2, basically 0. And then you can try to fit these parameters, how long it takes for the galaxy to become red. It's blue and it becomes red here. And what we find, again, fitting these spectrum, we find a relatively short time that it should only take about 400 million years for this stage of the star formation. So you can see that galaxy forming the cluster. It was happily forming star here. It hit about half R200, and then the star formation plummeted over 400 million years into 0. So basically, from this spectroscopy, that's what we found, these 3 things, which I think I will just skip. Now, in the remaining few minutes, I want to look at the what happened when we look at far infrared spectrum, which tell us about star formation. Because when you have star formation, the very the ultraviolet light from the hot star heat up the dust that happen to be in the star forming region or in the galaxies. And then these dust will re-radiate in the infrared or far infrared because they're hot. And here I show a spectral energy distribution of different kinds of galaxies. These are regular elliptical galaxies which have very little emission coming from the far infrared. Here's a galaxy that's forming star around 1 to 10 solar mass per year. You can see that it has some hot. These are actually still what we call cool dust. But once you have a lot of star formation, like 100 or even 1,000 solar mass per year, you find that you have a bump over at a temperature that's equivalent to about 60 Kelvin. So we identify these as what we call from warm dust, this bump coming from the cold dust. And there are also these features which we think comes from PAH, which is polycyclic aroma hydrocarbon. And this is the optical spectrum that we've been looking at is around here. Here's the UV spectrum. So this is what spectrum galaxy look like from sort of ultraviolet from 1 micron all the way to 1,000 micron. Now, when we look at the SPISR data, the 24 micron is here. Redshift 1 is about 12 micron, which allow us to look at here, which tell us, based on the PAH feature, how much star formation there is. And this is what a typical 24 micron image look like. Each one of these, each one is an image, and this is actually the cluster that's pointed at. This is the center of the cluster. You can see in 24 micron, you don't see a cluster because there's not much star formation in the center of the cluster. But when we actually then, again, stacking all the 9 clusters together, computing using the 24 micron emission, the flux, to compute the specific star formation rate as a function of radius from the center of the cluster. So these are for different galaxies. These are massive galaxy, intermediate mass galaxy, and low mass galaxy. What we find is that as the galaxy come in, when they reach about 1 R200, there's a bump in the 24 micron emission, and then it drops. So whereas for the massive galaxy, it simply just drop off. So this is actually very interesting, is that what they're saying is that when a galaxy comes into a cluster, they actually spend a bit of time forming more stars, having sort of a last burst of star formation before the star formation get quenched and shut off. And this is, you can say, well, this is not quite what we find in the optical that I just shown a while ago. But that turned out not to be true. If we look at the paper before from the optical spectroscopy, where we use star formation based on O2. I scaled this so that it gives about the same size unit. You can see that you can see these bumps here, which when we looked at the optical data a few years ago, we didn't believe it is real. But now we look at the 24 micron, it seems to be it is there also. So something else is happening to a galaxy before it got shut off, especially for the massive, the less massive one. Now the last bit of data I'm going to show very quickly is from another space telescope called the Herschel Space Telescope. This is a far infrared telescope that was sent up there, I guess, maybe half a dozen years ago. It stopped functioning a couple of years ago already. So it only functioned for a little while because you need to have cryogenic detector. And we managed to get observing time for 3 redshift 1.2 clusters, 3 of those 9 clusters. And we observed them in 5 bands. So these are the wavelength, the observed band of the wavelength. And now, go back to the picture of the SED. The 5 band from the Herschel, when you redshift it to about redshift 1, is observing at these 5 wavelengths. So you can see that these 2 bands would be sensitive to warm dust from star formation, whereas these 3 bands will be sensitive to cool dust. Dust that have cooled off and basically with molecular cloud that not much star formation is going on. And the image of these clusters actually look like this. This is 100 micron, 100 micron image, 160 micron image, quite ratty. These real circles represent galaxy that we actually have redshift, and they're that's what these data actually look like. And they're very low signal to noise, and in the end, we can only really get reasonable analysis by, again, stacking. So what we do is that we take all the galaxies position that show 24 micron emission, which means they might have star formation. Whether we see it in 100 or 160 micron or not, we stack them together to increase the signal to noise. So stacking, and all these, we only do objects that we have spectroscopic redshift. And we end up with about 48 galaxies that we stack. And we stack them in, we separate the galaxy in different bins in the velocity versus radius diagram. This approximately measure the time since infall. The object that have fallen in the earliest would be this bunch, and then the next set, and next set, and next set. So they're basically 4 different bins in the distribution in the phase space, and each one, as you can see, there are not many galaxies, but enough to give us some results. So what is plotted here is the observed wavelength, and the rest wavelength is up here, approximately, since they're not identical redshift. Here's the flux, and these are the galaxy in the 4 different bins that I've shown before. You can consider that this one is closest, that have fallen in the longest, this one's the second longest, and this one's the newest, and this one is the next newest. And there are 5 points for each SED. We fit a single temperature black body to it. And you can see that the one that really stands out being different is this one. These 3 have peaked basically similar, so the temperature is similar. And they are at where the warm dust from star formation is, where this is more from the cold dust. We can also do this for galaxies that don't belong to the cluster, and you see that they actually fit more or less similar to these. So these are actually the first determination of dust temperature, certainly for cluster galaxy at this kind of redshift. And they're not easy to do because you need a space telescope to do this. You cannot make these measurements from the ground. Now, we can use those black body curve and make these measurements, convert them to star formation,